Okay, in this lecture, we're going to begin in a new chapter. This is chapter 5 on integrals. So in this is going to be the next most important topic in calculus. Calculus can be roughly divided into two areas. There's an area on where you learn differentiation, and this is typically called differential calculus. And then the other thing that most important topic you learn in calculus is integral, and then that part of calculus typically called integral calculus. So what's the idea behind an integral? Well, the motivation for this idea, this concept of integral, the integral or integration, is finding areas. So we know how to find areas of various shapes. So in fact, let me share my screen now so I can show you what I'm seeing. So the idea is this is 5.1, this is the distance and the area problem. So the idea is that we know how to find the area of pretty common shapes like a rectangle. So the rectangle is just the base times the height, length times width. The area of this triangle is just 1/2 base times height. And then you have this other shape here. Um, and that area can be computed by basically breaking the shape into parts. So we have these four parts, and these will be triangles, and then you can find the individual areas of these things and add them. So area is additive. You can, if you want to find the area of a whole, it's the sum of its parts, right? Um, so that's all nice and fine. But what if we have something with a little bit different shape? So suppose I have a function, in fact, and let's just assume it's positive. So it's a function defined from A to B, and then you can plot the curve associated to this function. And and then you can look at this line right here at A, the vertical line at A, the vertical line at B, and then the curve, and then of course the x-axis. And this will be the boundary of some region, and it has some area. So the question is, how do you find this area in general for some, shapes that aren't ones we're accustomed to? So like, for example, the rectangle or the triangle or something like this. How do we find in general? What is the general procedure for finding area of more complicated regions whose boundaries are more complicated than these examples over here? Well, the idea is to do some sort of limiting process and to do some sort of computation about averages too. So it's going to look a lot, well, the idea behind it is going to be similar to the idea of a derivative. So in a derivative, you take, so the motivating example for differentiation was to try to define instantaneous velocity. And to do that, you would basically compute a bunch of average velocities. So if you have a point in time that you're interested in, you want to find the instantaneous velocity at that point in time, you compute averages over intervals containing that time, and you find the average velocity on smaller and smaller and smaller and smaller intervals. And then you take a sort of limit, and this limit will give you the instantaneous velocity. So the average is not going to give you the instantaneous velocity. It's going to be the limit of the averages. And we're going to do basically the same thing here. We're going to approximate the area, um, and we're going to get better and better approximations. And eventually we'll just take a limit of these approximations. And this process is going to look quite a bit different than process for defining derivatives. And so you might think there's absolutely no connection or very little. Well, it turns out there is a lot of connection, actually, remarkably, a lot of connection between these two concepts. In fact, so the differentiation is an operation. You take in a function and you can the derivative is an operator, and it takes in a function, it gives you another function called the derivative. And it turns out you can do sort of the same thing with integration. You can integrate a function and it will return another function, and this will be the what you actually call the indefinite integral. Um, but it turns out that these two operations are actually inverses of each other. They, in a sense, undo each other. So this is going to be what's known as the fundamental theorem of calculus. So this is a very remarkable theorem or result that ties these two areas of calculus that seemingly have nothing to do with each other, but actually have a lot to do with each other. Let's think more about this approximation process for defining integrals, though. So here's just a simple example. It's always good to have a concrete model in your head. Always good to have a concrete model in your head when you're analyzing concepts, when you're trying to develop concepts. So just take your function y is equal to x squared, so the parabola, and suppose we want, so we have this parabola, and we want the area from 0 to 1. So we have basically the y-axis, so we have this point right here, and then we have this line right here, the x-axis, and then the curve itself. They bound an area, they bound a region with an area, and we want to find that area. Well, if we're going to approximate the area of this sort of unusual shape, we should be approximating it with things whose areas can be computed. And what is basically the easiest thing you can compute? A rectangle. So what we're going to do is we're going to approximate this area right here by rectangles. Okay, so we'll just draw, so what we can do is we can take this interval from 0 to 1, we can chop it up, so we can divide it into 4 strips, and so this will divide it into 4 vertical lines at these points, at 1/4, 1/2, 3/4, and then so this will define when you're basically taking the interval from 0 to 1 and you're like subdividing it, and then you can um look at rectangles whose height is determined by the graph of the function. So the height of this rectangle is going to be 1/4 plugged into your function. So I guess that'd be 1/8. So this will have base of 1/4, and then height right here will be like 1/8. And then this will have a base of 1/4 also. So what we're doing is these rectangles will have equal widths. Their heights are going to be different though because they're determined by the graph. So this will be also be a base of 1/4, and then we're going to plug in 1/2 now into the function to get the height of the rectangle. So we want it to like these rectangles to be kind of built from the curve itself. So we want to plug 1/2 in there, and we get 1/4. So this is like at a height of 1/4. So, and then you can do the same thing here. You have this length right here is 1/4, and you plug in 1/3. The right endpoints. We're notice we're plugging in the right endpoints of this subdivision right here to get the heights of these rectangles. And then what you do is you just find the area of this rectangle, find the area of this rectangle, this one, and just add them up. And you might think, well, that's a pretty poor approximation. It's going to be over. See, like there's this, look at how much of it is over right here. You get this piece right here, and then this piece here, and this piece here, and this piece here. So this is an overestimate of the area. That's okay though. It's going to turn out that that's perfectly fine. We'll do better. Divide it up even more to get a better approximation. But first of all, let's kind of write down what's going on here in this case, and then we'll look at a better approximation. So we're going to approximate the region. So let's see. So so let's just summarize what we're doing. We're going to approximate each strip by a rectangle that has the same base as the strip and whose height is the same as the right edge of the strip. So in other words, the heights of these rectangles are the values of this function at the right endpoints of these subintervals. So that's what I was explaining. Basically, you take the unit interval 0 to 1, and you're going to subdivide it into these four sub intervals, and then these will be like the base of your rectangle, and then you're going to plug in the right endpoint of each interval to get the height of those rectangles. And then so now each rectangle has a width of 1/4, and these are the heights: 1/4 squared, 1/2 squared, 3/4 squared, and 1 squared. So now we're going to let R4 be the sum of these areas of these approximating rectangles. So then R4 is going to be 1 base times height plus of the first rectangle, base times height of the second rectangle, base times height of the third rectangle, base times height of the fourth rectangle, and this will give you 15 over 32, 15 over 32. So now, as you can see from the diagram, though, this is an overestimate, so we'll call the area of this region A. So A is some number, it's gonna be less than this number. So we need to do a better approximation. Now, there's a point here. We could have, sorry, we didn't have to choose the left endpoints of those subintervals. Sorry, the right sub endpoints of the subintervals. We could have chosen the left sub endpoints of these subintervals. And in this case, we would have these rectangles approximating the area. So what we'd have is like base times height, but this rectangle has no height because we're using the left endpoint, and then base times the height. So you plug in this left endpoint, this left endpoint, and then this left endpoint right here. So then you can approximate the area by using these rectangles. So it'd be base times height, so 0, because we're using the left endpoint of the interval. And then base times height plus base times height plus base times height of these other rectangles. And you get this approximation, 7 over 32. But now you can see from this diagram, however, this is going to be it's going to be a lower bound. It's going to be a lower estimate of the area. So the area is somewhere between these two numbers. But if we do, so they're just these endpoints, these bounds just approximate it. So the actual area, this area right here, the actual area should be somewhere between these two numbers. And so the idea is we want to like get better and better approximations to figure out what this number can be. So we can take more strips. And this would be so this would be how many subdivisions? I guess it would be 8 subdivisions, yeah. So these, yeah, 1, 2, 3, 4, 5, 6, 7. Oh, and then 8 over here. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this is gonna be these 8 subdivisions. So that's gonna probably be better, this approximation. And so you would have the subintervals 0 to 1/8, and then I guess 1/8 to 1/4, I guess. Maybe they actually write the intervals out somewhere. No, they don't. And then 1/4 to add 1/8 to that. Now you get 3/8, I guess. And then you get 3/8 to 3/8 plus another 1/8 would give you 4/8, which is 1/2. And then you do 1/2 to a 1/8, which would give you, I guess, 5/8. You get the point. It's gonna eventually get down to like, it should get down to 7/8 to 1. And so you have a bunch of subintervals. These subdivide the interval 0 to 1 into 8 pieces. And you can set these approximating rectangles up based on either the left endpoints or the right endpoints of the subintervals. And now this one right here is always using the left endpoints is always going to give you a lower bound in this case. And then using the right endpoints is going to give you an upper bound. But you can see that this is a lot better. This is more fine grained, this approximation. This one right here is a more coarse approximation. So it's poorer. This is again, this one right here is a more coarse approximation, so it's much worse. But we're getting better. We're getting a better idea of the area using more rectangles. So I guess what we get is this one's 2.1875. This is 2.73. So this is it's pretty big. It's significantly bigger, this number, and this is than this endpoint right here. And they have 0.46875. So this is actually much smaller than this number. So we're like these numbers, what you would say is like these endpoints, these upper and lower bounds, like which are computed using more and more rectangles, they're like converging onto the actual area. They're like approaching, we're taking a sort of limit. And that's exactly what we're going to do eventually. Eventually what we're going to do is we're going to say, okay, don't just take any partition of n to say 8 intervals, 10 intervals, a million intervals. Take a partition into n intervals. So we're going to take our interval and subdivide it into n intervals of equal length. So they'll have a length, each subinterval will have a length of 1 over n. In this case, each interval has a length of 1 over 8. And the other one, it was 1 over 4. But eventually we're going to just generalize it and just let it be 1 over n. And then what we'll do is we'll say that the area is going to be a limit of a sum of subrectangles as n goes to infinity, as we add in more and more and more and more subintervals. We're going to eventually think of it as like what it's going to eventually be is that we have like infinitely many subintervals in a sense. This is not entirely accurate. Well, we're going to have infinitely many subintervals. We're going to divide it into infinitely many pieces, and there'll be infinitely many rectangles, almost of like zero, like infinitely small width, but they'll like perfectly approximate the area. It'll give you the actual area. Let's see. So now you can see, and that's what we're actually going to do in this part right here. Actually, let me see. So we want to show that the region S in that example, we're gonna instead of we want to show that if we approximate it by sums of n division point, we divide the interval up into n points. We want to show that we can get this number to approach 1/3, which will be the actual area. So here's what we're gonna do. We're gonna imagine like we have. I'm sorry, hold on. I got dogs barking like crazy. Let me pause this for a minute. Sorry about that. Let me share my screen again. Let me just start over with this example. So let's see what it says. So yeah, we have this region that we were talking about under the parabola. And now what we want to do is basically what I was just saying, where we want to subdivide the interval into n points, and then we'll have n rectangles. And then we want to take a limit and show that this limit is going to be 1/3, and that's going to be the actual area. So I think we're going to do right endpoints. So what we'll have is, so if we're going to divide the area into n rectangles of the same length, then each rectangle is going to have a width of 1 over n, right? So basically, length of each subinterval, which are all the same, is going to be the length of the interval divided by the number of points you're going to use, which is n. So it's going to be just 1 minus 0, which is just going to be 1 over n, because that's the 1 minus 0 is the length of the unit interval 0 to 1. And then so now we are going to plug the heights. So we're going to plug the right endpoints into this function, and those will be the heights of the rectangles. So we have right endpoint. One of the right endpoints is going to be 1 over n. The next one's going to be 2 over n, 3 over n, and then finally up to n over n. So that is the heights are going to be just these numbers squared. So 1 over n squared, 2 over n squared, 3 over n squared, and up to n over n squared. So now this, we're gonna approximate it with n rectangles. So we have r over, sorry, r sub n. And so this is gonna be base times height plus base times height plus base times height, and then all the intermediate terms, base times height. So it's like the first rectangle, second rectangle, third rectangle, etc. Find, and then the last rectangle, the nth rectangle. And then what you're going to do is you just plug 1 over n, 2 over n, 3 over n over n, etc. And so you get 1 over n squared, 2 over n squared, 3 over n squared, n over n squared. And what we're going to do is you can notice that there is a common factor of, well, n in each one, and then also 1 over n squared. So we're going to factor out 1 over n times n squared. And when you do that, what's going to leave is just these numerators squared. So you get 1 squared, 2 squared, 3 squared, intermediate terms up to n squared. And then this will give you 1 over n cubed plus the sum of the first n terms squared. So now at this point, you're like, well, I don't know what to do with it, because eventually what we want to do, remember, is take this limit. So we're going to just like take an arbitrary subdivision of the interval, unit interval 0 to 1 into n subintervals. And this will give us like an nth order approximation or whatever. And then what we want to do is take n and let it go to infinity, and that will give us the actual area. But it's not clear how to evaluate this right here. However, there is a formula for the first, the sum of the first, has no, it has to say it's the sum of the squares of the first n terms. I think that's the right way to say it. So you have 1 squared, 2 squared, 3 squared up to n squared. It turns out that this is the same as this. So there's going to be a couple of formulas like this we're going to need to prove some integrals. But once we've gotten those formulas out of the way, integration will be a lot easier, well, slightly easier process. Um, so the idea is that we're going to proceed the same way with derivatives, where we had this like, intuitive idea, and then we wanted to try to mathematically formalize it into a rigorous definition, and then draw some consequences, and then develop some tools and techniques for computing things. And so we did that for derivatives. We're going to do the same thing for integrals. So now we're going to plug this. So we're going to replace this by this right here. So we have the 1 over n cubed times this whole thing right here. And then you have a factor of n cancels this one. So then what you have is n plus 1, 2n times 2n plus 1 over 6n squared. All right, so now what do we have? Well, now we're going to take this limit right here, because that's going to give us the actual area. So what we found out that r to the n, r sub n is this. So we're taking the limit of this thing right here. And what we're going to do is, well, first of all, we have this 6. So we have this 1/6. I don't know why they didn't just take it out of the integral altogether, but it's a constant, so you can just take it out. And then we have n squared, so we're going to divide one of the n's into n plus 1, and then the other n into the 2n plus 1. And what we'll get when we do that is now we'll further divide this n into the n here, and then the 1, so we get 1 plus 1 over n. And we're going to divide this n into the 2n to get 2, and then this n into the 1 to get 1 over n. But now we know how to compute this integral, this limit, right? We know that 1 over n, as n goes to infinity, is going to be 0, and this 1 over n is going to go to 0 as well. So we're going to have is 1/6 times 1 times 2. So 1/3. So that's the actual area. This is going to be the actual area right here. And you can do the same thing with when you take the left hand points in the intervals and you take a limit, you'll also get 1/3. So the area is going to be a limit of these approximating rectangles. And so here's the process. Like here's like a way to like visualize the process. You can see, we use 10 and 10, we divide the interval into 10 pieces, now 30 pieces, now 50 pieces. And you can see this area should actually approach as you let n go to infinity. Like you can imagine like these graphs are going down and down. Like you have these sequence of these graphs or regions, in other words, I guess, approximating the actual area of the region, and you're going to let n go to infinity to get the actual area. So you can see that this is a very good approximation. It's not going to be the best. It's not going to be the actual error, but it's getting better and better. Here's the lower limits. So you have this one, it's decent. This one's better, and then this one's really good, actually. All right, let's see. So now we want to kind of generalize what we've just done. So let's try to generalize it to so just any region. So suppose we have something that looks like this. So we're going to subdivide the region S into n strips of equal width, just as we did. So we're imagining that this function is defined from A to B. In the example, it was defined from 0 to 1. Um, so if these subintervals are all of equal width, we need to take the length of the interval and divide it by n to get the actual width so that they're all equal. So we have like n pieces, n strips. And so we'll call this width delta x. This is going to be like a change in x, really. Do want to think about it that way. And it's going to be the length of the interval. So b minus a divided by n. So these will be the widths that we're dealing with. And then we're going to have that these strips are divide the interval into n subintervals. So we'll have these intervals x0, x1, x1, x2, x2, x3, all the way up to xn minus 1 to xn. Don't know exactly what these points will look like. It doesn't really matter a whole lot. Well, actually, you can work them out. I'm sorry, I have mistaken. So what you want is you want the first interval, subinterval, x0, you want that to be A. And then in the last interval, you want the right endpoint to be B because you want every point in the interval contained in one of these subintervals. Notice these subintervals are going to be they're only going to have one overlap. They're going to be mostly disjoint. So like this interval right here and this interval right here, they intersect at this point right here, x2. But for the most part, they're disjoint. They only have intersect at one point. And so now you can actually work out the right endpoints, the rest of them. So if we know what x1 is, x0 is just A, and x1 is just going to be the width of the interval plus the left endpoint, right? Because that's how you like get the whole interval, right? The whole interval is length delta x right here, right? And then x um 3 will be a plus x2 will be a plus 2 delta x. So it's like let's see, do they have a picture? Wish they had a picture. I guess I could just try to draw something. So you have like this is terrible. Let's see. I mean, maybe it's clear. So you have a is here. So a, which is x0. And then maybe all the way over here is b, which is going to be x to the n. And then you have like x1, x2, x3, and they're all equally spaced. And it just keeps going down. So now this length right here is going to be 1 over, it's going to be delta x, right? This length right here is going to be delta x. So to get from this point to this point, you have to move delta x. So that's why x1 is equal to a plus delta x. Now to get from to this point right here, x2, you got to go delta x and then another delta x. So you have to go 2 delta x. So x2 is going to be a plus 2 delta x. And then to get to x3, you start at a, which is x0. You have to move a delta x, another delta x, and then another. And then you'll have arrived at x3. So x3 is going to be a plus 3 delta x, and so on. And in fact, what you can say is that xi, the ith partition point, these are going to be called partition points because you're taking the interval and you're partitioning it into subintervals. So the ith partition point, you say, is just in general going to be a plus I delta x. So if I is 1, you get this. If I is 2, so if you're talking about x2, you get this. If I is 3, so you're talking about x3, you get this. So this is the right general formula to talk about the I partition point. And that why it's important to describe these points is because these are going to be our right endpoints, our right endpoints of the subintervals, and we're going to evaluate our function at these points to get the heights, right? Yeah, so here in general, the I partition point xi is a plus I delta x. And now we want to approximate these strips. So we have like these strips here. The ith strip, si, um, we want to approximate the strip with this width here and then the height f of xi. So this will give, so we need to be able to describe these red endpoints. That's why we wrote out xi right here. And so now if we approximate with n rectangles, so and we're using the red endpoints, we'll call it Rn. It's going to be f of x1 delta x. So this, in this case, this is going to be height times width, and this will be height times width plus height times width. So we're adding up the areas. So overall, this whole thing right here is area of approximating rectangle. And the same thing with this. This is going to be an area of a rectangle, and this is going to be area of a rectangle. And then we're going to add all these up. So it's going to look something like this, and this will give us an approximation. But now we want to be able to let n go to infinity. So we want these approximations. So it says, notice these approximations become better and better as the number of strips increases. That is, as n goes to infinity. So we wanted to we're actually going to just take this to be the definition of the area. It's going to be this limit right here. So the area of a region S that lies under the graph of a continuous function. Turns out you don't need continuous necessarily. I don't even know why they're putting continuous in there. Definitely continuous is good. You want continuous. Are you sufficient? Being continuous is sufficient for this concept to make sense. Then the sum of the areas, then the area is a limit of the sum of the areas of the approximating rectangles. So the area is going to be this limit right here. And it turns out, yeah, so this limit, yeah, so here's the problem. Limits don't always exist, right? If not continuous, limit might not exist. Or if it's not continuous at a point. So for example, oops, if you had something like this, 1 over x, and say you want to integrate oh, you want to find the area, say this is 1, this is 0. This is basically this process right here is integration. You want to find this region right here. It's not going to exist. It's going to be infinite. It's not going to be a well-defined area. So you need continuous. So this is 1 over x, which is not continuous at 0. You don't. So continuous will guarantee that this limit exists. So as I said, it can be proved that the limit in definition 2 always exists, since we're assuming that f is continuous. But you don't need to assume continuous. It's going to turn out that there's a class of functions for which this limit right here exists, and these are going to be called the integrable functions. They're functions which can be integrated. And it's going to turn out that the integrable functions is the class of integrable functions, the set of integrable functions, is way bigger than the set of continuous functions, way bigger. You can have some really awful looking functions, and this is part of the reason why you can have some really awful functions which are definitely not continuous, but you can still integrate them. You can still find this area. This limit will still exist. But they're as I said, they're not continuous. And so this is part of the reason why integration is a lot trickier, a lot more challenging than differentiation because these functions are not nice like continuous functions. They can be really awful. Um, and we'll see some of those functions. So this is the idea of a limit. So we're getting closer and closer to a more formal idea. This is a fairly formal idea right here. This is a good formalization of the idea of an area as a limit of these approximations. But it turns out we can do better, and we're going to do that in the next section. I don't know if there's much more. I'm not going to go over the distance problem. I'll let you read that if you want. But this is another actually interesting thing to consider. It will actually relate back to what we did in the very beginning when we were talking about derivatives and limits. The idea where we looked at problem of velocity. How do we define velocity, instantaneous velocity? We need this notion of a limit and to talk about limits of averages. This is kind of like the reverse problem. Like, okay, how do we talk about distance? If I know if I'm traveling at a certain velocity over time, and if the velocity is constant, then the distance formula is really easy, right? It's just how fast are you traveling as the time. But what if the velocity varies? So like your instantaneous velocity can change a lot. Well, you need to do this process of taking areas and computing areas and taking an integral. So in other words, so what we have is that the derivative of your position function gives you your velocity, your instantaneous velocity, but the integral of your velocity gives you your distance function. So that's what it's going to end up being. So I don't think I'm going to go through this. I'll let you go through it. It's basically the same sort of idea. I definitely encourage you to read this, but let's go back up here. Sorry, kind of jumping all over the place. So this is a fairly good formalization of the idea of area. Um, and we want to note that you didn't have to use left or right endpoints. You can actually just, to get the height of these rectangles, you could use any numbers in these subintervals. So you could take xi star. And so you can see, and it will still give you an approximation. It's usually easier to just use the left and right endpoints, but you don't have to. So like right here, it looks like they use a midpoint right here, maybe a point that's like 3/4 to the right, 1/4 to the left. Here's another midpoint, midpoint, midpoint. The rest of these are just midpoints. This is kind of like 3/4 of the way. Um, so you can use any point in the subinterval. In fact, that's what you want. To define the integral. You want this limit right here to hold for any choice of points in these subintervals. So you get these sample points. So this is a very strong requirement. You want this limit to exist for any choice of these points right here in these subintervals. But as I said, it will actually turn out remarkably, even though that's a really strong requirement. It's equivalent to just requiring the limit exists for the right or the left endpoint. That's all you need. So it's pretty remarkable that you can get away with that. All right, let's see. So here's just some notational convention. So we've been writing this out and it's kind of cumbersome. So f of x1 delta x, f of x2, so f of x1 delta x, f of 2 delta x, a bunch of intermediate terms, f of f of x and delta x. And so we just use this so-called sigma notation. This is the Greek symbol, letter symbol, sigma. And we express this sum right here with just compactly in this way right here. So then these equations 2, 3, and 4 can be written in this way. And then that formula we used, where we took 1 squared, 2 squared, 3 squared, it can be written compactly in this way as well. All right, let's see. Well, I want to go over this. So let's see, what does this example say? So we have this function right here, e to the negative x. and we want to find the area of the region that lies on the graph of this function from 0 to 2. I guess we have a graph somewhere right here. Yeah, here's a better approximation. So what we'll do is we'll how do we do this? We're using right endpoints, find the expression as a limit, do not evaluate it, and then I'm not going to do B. I don't care about B. This is about taking sample points to be the midpoints and then using 4 subintervals and then 10 subintervals. That sounds really annoying. You're going to see that these integral problems are really, really annoying when you're trying to prove integrals and compute integrals by definition. So you're going to want to really try to formalize this definition of limit or integral as fast as you can, and then start proving things because you don't want to like some general rules and techniques and tools because you don't want to have to rely on the definition. It's going to be really awful. So we have a is equal to 0, b is equal to 2. We're talking about the interval from 0 to 2. And then the width. So if we divide this interval into n pieces, each of which has the same width, this width delta x is going to be the length of the interval divided by n. So it's going to be 2 over n. And then so the ith so yeah, so we're talking about right endpoints. Yeah, we're using right endpoints. So the x1 is going to be 2 over n, x2 is going to be 4 over n, x3 is going to be 6 over n, and then just in general, xi is going to be 2i over n. And so then Rn is going to be the sum here. And now we have f of x1, f of x2, f of xn. So that's just going to be e to the x1, e to the x2, e to the, sorry, with negatives, e to the negative xn. Sorry, there's negatives here. I didn't say those. So now you can just plug in x1, x2, xn to get this e to the negative 2 over n, e to the negative 4 over n, e to the negative 2 over n over 2n over n. And then this is just the width of the rectangle. So these numbers right here are going to be the heights of our rectangles. And then according to definition 2, the area is just going to be this limit, right? So we can, and then we can, of course, write this more compactly as this sum right here. But you can't actually compute this by hand. Um, there's no way of evaluating this limit. You have to use, I mean, there may be a way, but it's not going to be easy at all. So you can use a computer to calculate this, and but it turns out that once you've developed more tools and techniques for computing integrals for computing limits of these forms, there's actually a way to get around it, and you can find um, the integral once we get to the fundamental theorem of calculus, actually. All right, I think that's going to be it. So yeah, so just read through this. I mean, I kind of already said what the idea behind the distance problem is that computing the distance is easy when you're traveling at a constant velocity and you travel a certain amount of time. You just it's just gonna be velocity times the time it took you to travel. That'll give you the total distance. And notice this is like height times width, right? Width times height. So this is an area. When you want to calculate the distance you're traveling, you're really calculating the area under your velocity curve. You have this velocity curve. So in other words, like you have this velocity curve. It's like if you're traveling at a constant velocity, it's going to be a constant height. So this is like v of t. And actually, let's say there's nothing over here. Oops. Let's say you just start here and you just at a constant velocity. And so this is time 0. This is t-axis. And then you travel up to here. And this is like, I don't know, like t sub 0 or something, some specific time. No, maybe not. Let's call it a, I guess. And then so the time you took to travel would be the length of this interval times this height right here, space times height. And this area is going to give you how far you traveled. But if you don't travel at a constant velocity, So this is our one of your velocity curve. So you're kind of moving up, then you just increase, you're accelerating and then decelerating, etc. And you want to find the total distance you traveled. You would have to compute this area right here. And so you would need to basically go through the whole procedure we went through. So if you're traveling at a constant velocity, finding the distance is easy. It's just like computing the area of a rectangle. But if you're not traveling at constant velocity, you have to compute the area of this curve right here, under the curve, I should say, under your velocity curve, and that will give you the distance to travel. So it's a little bit trickier. All right, that's all we have for today. So let me stop sharing and stop recording.